Okay, so the way to get everybody's attention is to give a homework assignment, and so I didn't want to rush it the first week. So here we are in the second week. So I sent this out to you a little while ago, and I think probably after today's class, you'll probably have some idea how to do this, and it may take some into the lecture next time to make sure everybody's on the same page. So hopefully, have you guys in class been able to download the software? So that at least works. Yay. Okay, well, that's 2/3 of the battle. Okay, so let's read this together and see if we can make some sense out of it. So this homework assignment is to work with the Carrier HAP is Hourly Analysis Program software to predict the annual operating cost for an office building in Nashville, Tennessee. You have been emailed the basic HAP model of the building, and I think you guys had that in a previous. If you can't find it, let me know and I can send it out again. Let's see, you are to explore the annual cost of operating the building with different equipment configurations. The base model you have in the file supplied has a water-cooled centrifugal chiller with a dedicated cooling tower. And so I think actually what I sent out has probably all of the chillers in it. I just assumed that you made some on your own, but I mean, either way, you have to change the chiller assignment in the building and rerun, and you can get a report. You can get pages and pages of report. And really, you don't need very much of it, but it'd be good to look at all the stuff in the report just to kind of understand some of the capabilities of the program. And so I think when you create a chiller, this thing defaults to 42 degrees. So you got to be a little careful in the chiller definition that you set it to 44. And I did this on purpose just to make you get in and change something in the chiller model, you know, just to get a little more familiar with punching around in the software. You are to assume the model emailed is the base case or starting point for your investigation, so long as it has the water-cooled centrifugal chiller as that's the base case. That's kind of the standard design. And then we'll see how to make these. I mean, this is, once you have this thing up and going, I mean, this is like, I mean, just a few clicks here and there and bingo, you run it again. So it may look like a lot. The biggest part of the assignment is really to take the data and assemble an Excel sheet that compares the different options, really. Okay, so the first thing would be to investigate airside economizer, which then that's that free cooling with outside air. And there's two ways to control it. There's the integrated dry bulb control and integrated enthalpy control. And actually, I think there may be one other option in there. And I don't think we talked about the enthalpy versus dry bulb. I think I may have glossed over that the last class. What that's referring to is, you know, we have to make a decision. Do we want to minimize our outside air or do we want to maximize our outside air? And it has to do with energy content of the return versus the outside. Whichever one has, you know, and this is in a cooling situation, whichever one has less energy, we want more of because it's less mechanical cooling, less energy cost. Okay, well, how are you going to make that determination? Well, you have to compare something in the return air with the outside air. So the best thing to do is enthalpy control, because enthalpy is total energy. The enthalpy is the energy and the sensible energy, you know, just in the dry bulb temperature, plus the energy in the moisture content. And like in Tennessee, it may be cool, but it could be 95% relative humidity, and there's so much energy in the moisture in the air that you'd rather have warmer return air because it's dry, much drier. And so the best thing to do is you just have enthalpy sensors, and you know, you just compare. And then, you know, your economizer controls, if they're set up right, are going to take the one that has the least energy to put across the cooling coil. I mean, this, the terms sometimes sound complicated, but the concepts are really pretty simple. We just want to cool whatever has least energy across the cooling coil. Okay, well, so if you're too cheap to buy enthalpy controls, guess what? You buy dry bulb temperature controls and you just don't worry about the moisture. Well, in this day and time, probably not many people are doing this. When I was your age, enthalpy sensors were not very good, and they were expensive, and they went out all the time. So 30 years ago, people would just say, screw it, I'm going to control on dry bulb temperature because I'm tired of replacing these $1,000 enthalpy sensors 3 times a year. It ain't worth it. So, but these days, most likely you're going to make those determinations based on enthalpy. Okay, so that's what that's about. And, so you just, yes, sir.
So the enthalpy sensors, do they last, how long would they last nowadays?
I don't really know. It's been a long time since I've been out there in the field. And, for when I first started in this, I was director of physical plant at University of Tennessee Medical School in Memphis. And I was out there looking at the equipment and seeing all the purchases and all that stuff all the time. And you know what? When I sit in this office in here in Brown Hall, I don't know, but they're much better than they used to be. We'll get together with Andy Loftus, who is the chief campus mechanical engineer, runs the chiller plant, and that would be a great question for Andy. Because when those sensors go out, he has to approve the purchase of the new ones. And he knows, because he's sitting there running that plant. When they have a problem, they bring it to him. But I would say probably years these days. But that's not a very well-educated guess, to be honest with you. Good question. Okay, so each air handler, and and I'm gonna pull up this building here in just a second, but we've got north, south, east, west, and core zones. So we've got 5 air handlers. So you just have to go in and get to the economizer control switch on all 5 air handlers and set them the same way. Make sure in the base case, everything that doesn't have an economizer, and then run the integrated dry bulb, get a report, run the integrated enthalpy control, get a report, and then do all your subtraction and see what difference it makes according to the HAP model. Okay. So you do that, and then you want to investigate thermostat setback control. So I say use 73 occupied and 77 unoccupied for cooling, and 71 occupied and 65 occupied for heating. Now, I would suggest before you run your base case that you go check your thermostat settings and make sure that, so in that base case model, cooling should be on 73 all of the time, and heating should be on 71 all of the time, because we don't have setback, okay? Now, you can control that with a schedule, and we'll look at that again. We did some of that last time. And so then your occupied periods, where we need the more comfortable settings, are going to be what, 6 a.m. to 8 p.m. Monday through Friday, and 8 a.m. to 4 p.m. on Saturday, and we're going to say the building is down on Sunday. Okay. So you just run one case. Well, you've got your base case where you don't have your setback, and then you change the schedule, the thermostat schedule, where you have the setback, and run that and look at the difference. Setback, usually this much setback will make a fairly significant difference. Should. Okay. Run the base case with the cooling tower fan changed to variable speed control. So that's just one switch in your cooling tower, and I'll show you where that is. So you know, and you don't have to run these in order. You might want to run that one first because you run your base case and then just, but be sure and turn the variable speed off for the rest of them, because we want to look at these things all versus the base case. If you're not careful, you'll wind up with some hodgepodge because you forget to turn stuff off, you know, and that happens. And then run the base case with the chiller type change to an air-cooled scroll type chiller. Okay, so air-cooled means you won't have a cooling tower associated with an air-cooled chiller. So cooling towers are required for water-cooled chillers. I emailed you out the Nashville Electric Service GSA data, and in that file, there's a rate number 1, a rate number 2, and rate number 3. So just go down, skip the number 1 and number 2, and go down to the number 3, and that's your electric rate. And then these are actually last year's gas rates for Cookeville, but what the heck, it doesn't matter. And then, but you know, we'll have to figure out how to put these rate structures into the program, okay? And so I'd say basically a week, I'd be looking for those. And, you know, if you can just email me that Excel sheet is good enough. I don't want to see all these HAP files. HAP will generate files left, right, and sideways. You know, these computers are good for that. Well, you know, I'm thinking they may have improved the internet in here, because I haven't had a weak internet signal in, what, over 12 minutes. That's pretty good. It wasn't this class. Last week in the afternoon class, the Wi-Fi, the recording bombed because the Wi-Fi in the room bombed because it was so bad. So I complained. Then Thursday, I streamed it from my cell phone because I didn't trust them in here. So the trials and tribulations of it all. Okay, so let's fire up the HAP program while we're having so much fun here. Okay, so, and I'm gonna go ahead and start from scratch, just to let you guys see this. Now, if I'd find Carrier, there it is. And hourly analysis program. Okay. And so once you download this and save it, then it should appear here. But I'm gonna go ahead and retrieve it from the archive just one more time to show you, because you may not have opened the file yet. So if you already have and have saved it, you know, you can pick whatever name you want. So I've got it here, but I'm gonna go ahead and pull it off of the, and you know, you can leave these. It looks like they're wanting to default to 13. ASHRAE 62 ventilation standard and 90.1 energy efficiency standard. So you can do that. And so I don't have anything in there, so I'm going to go over here, project, and then archive and retrieve. I'm going to retrieve the archive. Yeah, let's see, documents, I put it in the homework folder. Homework 21, there it is. So I just double click and it says, do you want it? I want it. Bingo, it's there. So I'm gonna save this project, save as, and I'm gonna put 21 on here so I can keep them straight. Now, next time I fire up this program, I won't go to the retrieve. I'll just pick it out of that list, click it, and bingo, it'll be there, okay? But again, if you want to email this model or something, you have to do the archive, because it includes all the weather files. It includes a bunch of files that it has access to on your computer. But if one of you share a model with somebody else, you may not have those files associated with, you know, that if you just sent the saved version of the file. So, okay. So we were doing some of this last time. I think we can look at spaces real quick. You know, this was our building. I guess I can pull up the, there it is. Yeah, this was this guy, you know, 600 feet, 370 feet, 40 feet depth on all these things, 290 here. Hopefully all that adds up. My biggest challenge is to get my square footages right with my dimensions. And then we had the elevations where I just stuck in some windows. And then this is looking at the ends of the building. And I never even put any doors in this poor thing. So I guess it's a fire trap. Well, it can't be a fire trap because you can't get in it unless you crawl through a window. But anyway, we could put doors and stuff in, but for our purpose, it really doesn't matter. Okay. So these are the square footage, and these spaces have all been built, but I think we looked at maybe south. Let's look at east today real quick. So give it a name, you know, calculate your square footage, put in 12-foot ceiling heights. Building weight is brick and block, so estimated it to be 130. And then tell it what type of space it is, and this is the ventilation requirement. So for every person, it's going to put in 5 CFM, and then for every square foot, it's going to put in 0.06 CFM. So this zone would be 0.06 times 11,600 plus the number of people in there times 5. And that's the ventilation that would be required by the 2013 version of the ASHRAE ventilation code 62. Okay. Internals, you know, I said lights. I think I just use a 0.9 watts per square foot for most of the building. Ballast multiplier, I just left it 1. And then this is my lighting schedule. This says for each hour of the day, what fraction of these lights are on. So what it's going to do, it's going to take this 0.9, that's because that's watts per square foot, and it's going to multiply it times 11,600. Let's see, did I bring, I don't think I got in here with my calculator, but whatever that number is, say it's 9,500, whatever. And then it's going to, for each hour, it looks at that schedule number, and that schedule says, okay, 20% of the lights are on. So then it takes that times 0.2, and that's the amount of lights that are burning in that space for that hour. And then it goes through hourly and figures out what the loads are. So, I mean, it's doing a lot of work for you in there. And so task lighting, I didn't put it in. Equipment wattage, I put in 0.15 watts per square foot for computers and, I don't know, water coolers, copiers, whatever. You know, when you're doing a real design, sometimes you have that detailed information, and you can say, okay, well, I'm going to have, 15 people in this area. Each one's going to have a computer. You know, you look up specs on typical computer wattages, which is not much these days. In the old days with the old, like cathode ray tube video stuff, like the old TVs, man, I mean, they were several hundred watts a piece, you know, or more for a big one. But these days, the computers are pretty small, but, you know, copy machines and other equipment, motors, anything that's in the space that's dumping heat, that becomes internal load, and you have to, you know, tell the program about it. So you can put it in here. You could put in wattage or watts per square foot, and then you have to have an equipment, a schedule to tell it. Again, it's going to do the same thing. Here, it's going to take that 0.15 times the square footage. That's the peak, and then it's going to look at the schedule to see how much of that's operating during any particular hour. Okay? I got 60 people doing office work. And then I have the people scheduled. And you can see the sensible and latent loads. And you've got other places you could put in other sensible, miscellaneous sensible or latent loads, and those, the units on those would be BTUs per hour, but the others went in watts or watts per square foot, but BTUs per hour works just fine, and you would schedule those. So that's, once you kind of get the concepts down, I mean, that's what I like about this program. It's pretty easy to teach students. You guys are so good. By the time you get that senior year, you pick up this stuff pretty quick. And so it's, Train's program is called Trace. And we have, I don't know where we are on licenses. Trace makes licenses difficult. They have a license server, and every time you fire the program up, it has to go and bounce your registration number off some server in Wisconsin, and all that has to mesh up, and trying to get that. And then I can't just put it on all of your laptops. It has to go in the computer lab, and then every year it has to be re-upped, and I got to work with IT, and I send you an email and you get the program for life. Now I will tell you, more people out there in the real world of HVAC design use Trace than use the HAP program. Some people use the HAP program, and it's fine. They've been benchmarked, and they've all gone through, they're both certified for lead studies and all that sort of thing. And so they're both very good tools. Trace seems to be the industry standard more than HAP, but I can't deal with it in this setting. I've tried once or twice. I've got like a 80 or 100 seat license, but every time somebody wants to use it, it's like, well, it won't open. And then I got to go through the help desk, and it's just one thing after the other. So anyway, I've kind of let it fall by the wayside. I guess you could say I'm getting old and lazy, but you fight these battles so many times and you go, I'm done. I ain't doing that again. So whatever. Okay, so here you put the exterior exposures. So the only walls that go in are ones that are losing heat. And now if it's losing heat to an unconditioned space, we have to put in a partition. And that can happen, but that's usually pretty minor. Maybe you got the boiler room under you or something, and so you got to do something a little bit for that, because you want to have that heat transfer in the model. But generally speaking, these are exterior exposed walls. So, let's see, can I get to this? So this is the east. So let's go up here. So if I look at my east zone, say all these walls are interior, so I only have this east facing wall to put in, okay? So that's it. And, I said it was 12 foot tall and 270 feet long, whatever, do the arithmetic. And you put in the gross area. When you put windows in, it will subtract the window area out of the wall area for you. So that's very nice. And then I had 10 of these 8x6 windows that we had defined previously. And say you can only put 2 window types in one wall, but you can have more than one east-facing wall. So, if you felt like you needed to, you could divide the east-facing wall into 2 or 3 pieces, but you only get 8 total. So, there can be a little limitation there. But, if you just get the square footage of glass and the type of glazing correct, you're going to be fine. This is not that exact a science. And then we don't have doors. So that's pretty much it on this guy. And then roof, I was lazy. You can put in, if it's sloped, you put what compass direction the normal coming off the roof would point. Would it point north or whatever, like this? This building has a sloped roof, so this side's actually pointing, I think that's north, and I think that's south. So I'd have to put in, I'd put in a north. I put in half of it north and half of it south, and slope and pitch and area, pain in the rear. so nice to just say horizontal, you know, and then it becomes the floor area, but it's there. If it's not horizontal, you put in slope, and you can have skylights. You just have to, like, you could define a skylight right here. We haven't done that because I didn't put any in this model. Infiltration. This is ACH is air changes per hour. Okay, so that's the volume of the building swept out, or the volume of this particular zone. So it's what? It's 11,600 square area by 12. So that would be the volume times 0.3, and that's going to equal 696 CFM. So that says I've got that much air leaking into my structure, I guess around the cracks and crevices, or, you know, damn contractors aren't any good anymore, whatever. You know, the wind blows. Now, good old Brown Hall, man, the wind blows, you go over there and stand by those windows and you can feel it coming through, you know, because they're single pane and they're, what, 40 or 50 years old, and they leak like a sieve, you know. And like you go in the hallway, how many air changes per hour do you think we get down that hallway coming in those main doors and out on the ends? Oh, probably 3 or 4 or 5, especially on a windy day. You get lots of air change. So, you know, it takes some time to get used to air changes. The old, when I started in this business, they told me that 1 air change an hour was probably my grandmother's house. Old white frame house, 2-story, single pane windows, doors didn't fit all that tight. And that's about 1 air change. So if you got a brand new, really tight building like over here across the street, it's probably 0.2, 0.3, something like that. It'll be down there. So this one, you know, I mean, I made this really pretty good, even though it's almost 700 CFM, but, you know, you take a 270-foot exterior wall with all those windows in there and the wind blows up against it, you're going to get some air. And air, you know, most wall constructions leak a little bit, you know. I mean, you don't necessarily think about it, but I mean, you get a 20-mile-an-hour wind blowing on that face of a brick and block building, you're going to get some air leaking through. And then, so I typically put in the air change number. If you look in the HVAC or in the ASHRAE literature, there is what they call a crack method. And oh my goodness, you can look up typical indoor-outdoor pressure differences. You can look at cracks. You can measure or calculate the crack length all the way around every window on the face of the building. And then you have to make some assumptions anyway. I did that once or twice and spent 2 hours doing calculations and then had to make a bunch of assumptions. I said, well, crap, why don't I just assume, you know, half an air change and I'm done? Because I'm making assumptions one way or the other. You know, now maybe the crack method might be a little better, but I'm way too lazy to do that. But anyway, there are some other techniques for estimating. And now, you know, if you have a constructed building, you can do an infiltration test. They call it a blower door test, where, you know, they'll come in and they'll put a blower with a variable speed on it, and then they'll pump up the pressure difference from the interior to the outside to a set like, I don't know, 0.3 of an inch or something like that. And then based on the speed of the blower, they know how much air it's putting out because they've calibrated that. So if that's what's going out and that the pressure is stable, if that's what's coming out of the blower being blown in, that's what's leaking out of the building. And so, yeah, you can measure it in an existing building, but the poor old design engineer is trying to estimate it on a building that ain't been built, you know. So, you know, the standard of care, I think, in a legal proceeding would be that you have to have some reasonable accommodation for infiltration load. If you left it completely out, you would be negligent. But, you know, if you went through this and said, based on, you know, my experience, my firm's experience, for this type of building, we use 0.3 of an air change an hour. And I mean, it's hard to argue with. At least you got a story to tell. So that's infiltration. And then if you, when you first bring up the tab, it'll be clicked here. And if you run that, then a lot of times you don't see infiltration in your loads, because when the fan is running, it zeroes out the infiltration because it assumes the building is pressurized by the operation of the air handling system. Personally, I don't like that. If I put in infiltration, I want to see infiltration. Don't tell me to put in infiltration and then I look in the load sheet and it's not there. I go, well, crap, you know, it's not in there. I don't like that, you know? So anyway, that's my personality, but I'm sure plenty of engineers would run it the other way. Floors, again, square footage, type of floor. I said this was, for our building, simple slab on grade. It could be slab below grade. You could have a crawl space unconditioned, or you could have, you know, it could be like the second floor of this building where you have conditioned space underneath it, in which case you probably don't have much of a floor load. U value, that's a default. I usually don't change it. Exposed perimeter, you know, is that right? That might be wrong. I've had, what is that? No, 290. I was thinking, I guess it's 370 on this side, 290, that's right, okay. Because that's the exposed perimeter, the edge of the slab that's losing heat directly to the air. So that's accounted for there. And up north, they actually put insulation on the outside of the slab to reduce the heat loss. You know, probably doesn't do much in the summertime, but in the wintertime, you know, when you have enough cold temperatures, and it also keeps the cold from penetrating up under the building through the slab, which, you know, it can get cold enough to cause condensation on floors. I'm gonna have a seat here. If I don't kill myself first. Maybe. Good Lord. I tell you, that knee starts barking after a little while. All right, let's continue on here. Floors, partitions, we don't have any here, so that's okay. So you go through that for each one of those 5 zones in this case. And so that's the space, and then we have the system. So we'll go ahead and do east here. Okay, so you just, first of all, you just give it a name, pick whatever you like. Something creative like East System. Engineers aren't really very creative. My wife tells me all the time. You know, and then what type of equipment? I've got a water chiller in here, so, you know, I don't think I have much. I think if you're gonna have a water chiller in chilled water, you're gonna have to have, what's that, chilled water air handling units. So I'll pick that. And then single zone. So this is basically saying how many thermostats am I going to have? You know, so I mean, I could say I'm going to put a bunch of small boxes, VAV boxes or whatever in this thing, and I'm going to have 4 or 5 different thermostats. But for simplicity, each one of these areas, I've got 1 stat. So it's, and I'm doing constant air volume. So you've got all kinds of different potential here, you know, and, you know, it's just, depends what you're trying to simulate. But for this example, I'm just trying to do something simple. Okay, so, and then you've got all these possibilities. Notice economizer is not checked. So if I run this thing the way it is, it has no economizer. Okay, so when you go back to run that number 2, you're going to have to check that box and then give it a little bit of additional information. And then you can click on each one of these. It comes up on the ventilation tab. And airflow control is constant. It's a constant air volume. You could schedule for your ventilation air. You could have demand control ventilation. Demand control ventilation is varying the outside air based on the demand in the space. So you can have CO2 sensors, or you can have, if you have a building automation system, you can schedule it. It could say, for example, this classroom up until 8 o'clock in the morning, I don't have any people, I'm going to assume. All I have is the square footage. And so then that's all the ventilation air that would be required. And now if the whole building is not occupied, you're not required to ventilate. But a building like this is really potentially people here 24 hours a day. So if you were controlling this building, you'd probably want to keep the, some ventilation going. Okay, so we'll just look at these, and we'll go back and we can add that economizer. But so cooling coil, how are you going to control it? You can do supply temp of the water, supply CFM or CFM per square foot. So this is what it defaults to. Or that's the airflow, or that's for the airflow into the space. Bypass factor, that's a coil parameter. Basically what it says is that 90% of the air gets cooled to the coil face temperature, 10% of the air gets through like it didn't get conditioned at all, and then we mix it together to get to 55 degrees. So that's kind of what a bypass factor is. And 10% is kind of a standard industry number, but you can run whatever you want to. Cooling source in this case is going to have to be chilled water because we've got a chiller. Again, we're going to allow it to cool every month because I haven't clicked any of these buttons. Capacity control, cycled or stage capacity, fan on. So that would say I'm going to run the fan when it's occupied, and I'm going to use like a chill water valve to modulate coil capacity. So, with VAV systems, we might let the coil run and modulate the airflow across the coil, sort of a thing. So you got different control options. Heating, similar type stuff. This is the default, I left it there. Okay, hot water. And so when I tell this hot water, then when I get to the plants, I have to put a boiler. I got to put a hot water boiler in, or where in the dickens did the hot water come from? So that'll show up later. Supply fan, you got different fan types, all kinds of different stuff. Forward curve with variable frequency drive, all kinds of stuff. So just keeping it simple. Okay, so in this, on the fan page, you have to put something in here to get fan heat as one of your loads. And that's one thing I always bitch about. I want you to make sure that you put something in here. Now I put the fan static, and say it calculates an airflow and a static, and it's got something for fan efficiency in there. I don't know if we put they say I've got overall efficiency 54%. So it can calculate an energy use for the fan, and then that's heat that goes into the airstream. So that's heat that the chiller has to remove. So that becomes part of the load that the system sees. But if you don't put, so this defaults to blank, if you don't put something in there, then you won't get any fan heat. So you can put in any of this stuff. There's some, ASHRAE 90.1 has, its minimum or maximum allowable. You can put in CFM, total static, you put in brake horsepower, whatever you want, and it can handle it. But so, if you haven't done any duct design, then you probably don't have a feel for what static pressures are needed. 1.2 is not terribly high. For, like a big high-rise building, they may have up to 2 inches is considered low pressure, and something like 2 up to 7 or 8, I'm not sure the transition is medium pressure, and above that is high pressure system. So in a big high-rise building, like a great big building, a lot of the air might be distributed throughout the building in high pressure systems to keep the duct size down. but then you can't put that out of diffuser because it's too much noise. So then what they do is they'll drop the pressure till they get to the distribution close to the space, and then you've got low pressure stuff coming out into the actual space. That's pretty common. Okay, duct system. So do you have ducted return or do you have plenum return? Okay, a ducted return is probably, you probably figure out what that is. Okay, so the old 241 was a good place because to talk about this, because it used to have the drop ceiling and you could see the return register. So, a lot of times you do have a drop ceiling or something where or a return grill will be sitting in there. And the question is, does it have a duct? Or like if it's in a drop ceiling, you could just have the area above the drop ceiling and the fan is just sucking the air back. Say the air handling unit is up there above the drop ceiling and it just has an opening in the back and it's just sucking the return air right out of that area above the drop ceiling with no duct work. So, you have the drop ceiling, you have supply registers here and there, and then you just have some return grills. And so the air just, because you're sucking air, the return air out above the drop ceiling, it's a negative pressure. And so that'll draw the room air off of the ceiling back up through those return grills, and it just returns right back into the unit. You duct some outside air into that unit to get your ventilation air, perhaps. It mixes in the unit and it comes back out. So that would be a plenum return. Okay. Now, so when I first started, I did a lot of HVAC design for about 15 years. I probably stamped over 100, 120 projects. Most of them were fairly small. If you're from around here, Avery Trace Middle School was my biggest job. It was about, 65,000 square feet, which in the big realm of things is not all that big, but I mean, it's big enough that we had chillers and that sort of thing. And it was my first job and it was my biggest job. And it was one of my few chill water jobs. And I shared it with a fellow that passed away over here, Don Williams, worked in the manufacturing center. He was a technician, or a support engineer. He wasn't just a technician. Don was a sharp guy. And he was working for an architect here in town. And Don had been doing the architect's HVAC design for a while, but Don was a procrastinator. He was a big time procrastinator. And so, I mean, that was a 65,000 square foot job. He got to be about 4 months out from the end of the design phase, and he hadn't started. And, the stuff hit the fan, and this architect in town was a guy I used to play basketball with him, and he just said, "Hey, are you registered? You got your PE?" I said, "Yeah." He said, "Hey, you want to help us on this project?" And I said, "Well, sure, man. Do I get paid?" He said, "Oh yeah, I'll pay you." I said, "Well, if you'll pay me, I'm there, And so Don and I divided it up. I ran the loads, and he selected the chiller, and I kind of did the air side design, and he kind of did the water side design, selected the chiller and the cooling tower and all that stuff. And then it was interesting. We probably had 5 or 6 pages of mechanical, and there were pages that I would stamp, and there were pages that he would stamp, and then there were pages we would both stamp. If we both had something on the page, we would both stamp it. And that's the only job I ever really did like that. But that was my introduction, and I was much more prompt and on top of things than Don. So over the course of the next few months, I think Don kind of got fired and I kind of got hired. And I think Don was happy with that. He was pretty much at the end of his road with doing that stuff. So anyway, little war story there. Okay, so let's say we've already run the base case. We want to put the economizer in. Well, gosh, this is really hard. You check that box and you put integrated enthalpy control, integrated dry bulb, or non-integrated dry bulb control. So it comes up with this. And these are ultimate cutoff temperatures. So the way this comes up, We're definitely not going to go on economizer above 73 outdoor. Well, you can change that if you want to. You know, but so this gives hard limits to make sure that it doesn't open up beyond that. Okay, and we're definitely not going to open up at all at minus 60. So, you know, you're probably not going to have to worry about bumping into that one. But anyway, so that's how we put the economizer in. That's pretty easy. All right. Let's see, zone components. Now, these are all of the spaces that have been defined. But let's see, this unit is just east. So, you know, I click on this and put add, and it puts it over here. I mean, I can put any of them in here, but that's the idea that this air handling system is for the east zone, so I'm only going to put the east zone on it. So that's how you assign spaces. Now, you know, for example, you could have an office building and you can define, I mean, and they could all be a little different. And you could have like 10 different offices all on the east side of this building, and you could put them all in here. Now, the way this is set up, they'd each run on, there'd just be one thermostat, which there might be some bitching and moaning over that. You know, usually the meanest secretary gets the thermostat, right? Because the boss doesn't want to deal with it. He says, I don't care. You set it wherever you want to. I don't want to hear this, you know, whatever. Or you could go back and run multiple zones, and you could, you know, you could have 3 different zones, and you can put different spaces. Like thermostat 1 has offices 1, 2, and 3. Thermostat 2 has 4, 5, and 6. And then you can put that all under different zones on one unit. So you can have a multi-zone unit built up. So those would be the spaces. Thermostats. Okay, this is where we put in our thermostat settings. And yes, see, these thermostat settings are not really right compared with what I told you. Even though, I mean, I don't care. You can leave these for the base case. You can go ahead and leave these for the base case if you want to. I mean, I don't care that everybody has exactly the same numbers. I just want you to get some experience running this program. So the way this came up, so for my cooling, I've got 75 occupied and 80 unoccupied. Now, the program's going to go to the thermostat schedule to figure out which hours are occupied and which hours are unoccupied. If you say it's occupied all the time, then that 80 will never get used. You know, so you have to tell it that it has, you know, setback time that it'll go to the setback thermostat setting. Okay, and so in the heating, I've got 70 and 65. I think this is still true. This heating number has to be 1 less than the cooling number. I do not know why. It must be something in how they have this thing programmed. But if you try to set this on 75, it'll give an error. It won't let you. So anyway, throttling ranges has to deal with how they model the thermostat. Diversity factor. Direct exhaust airflow, are we exhausting any air? Like, is there toilet exhaust directly in this? And if there is direct exhaust, what's the KW of the fan? Okay, and here's my thermostat schedule, and this is the one I always forget. If you don't have a schedule in here, you click OK, and it'll come back and say, no, dummy, you got to give me a thermostat schedule. Supply terminals. This is not one I usually adjust. You could look into this. I'm not real sure. One thing you can do, if you hit function key F1 on this thing, let me see, can I find my function? I don't ever do these function keys. I think it. Yeah, you get the help. So it's built right in. And you get basically the manual. So, and it should be, see, it knows where you are in the program, and so it should bring up, like if you wanted the economizer, you could click on that economizer thing and then hit F1, and it'll bring up the economizer discussion. And it's pretty good. And then, you know, it's got related links and all that sort of thing that you can click on. So F1 brings up the help. Okay, so I'd say that's pretty good. Sizing data, I don't ever mess with this. If you have your own data, you can put in there, but I don't. And then equipment, let's see, changeover controller, I'm not sure what this is. What is this? Changeover schedule outside there. This would be if you have for a two-pipe system. Okay, I have not noticed this before. That's interesting. So, okay, so I don't think this is true, but it could be. There are systems like this unit in the classroom that just has one core. Now, in the dead of winter, we want hot water going through that core, right? Because it's going to get nippy in here, okay? In the dead heat of the summer, when it's 95 degrees outside, we want good chill water going through that core. Well, when we get into September, October, November, we get days that may be 40, 35, but they might turn around and end in summer and get up to 75. So, wow, we'd really like to have hot water at night and chill water from 9 o'clock in the afternoon until 5 o'clock or something like that. So that's what they mean by changeover. Now, these days, okay, well, for example, how am I doing time-wise? I'm just on a roll today, aren't I? You've got to figure out how you're going to change this over. Now, at Tennessee Tech, back in the day, and some of these units in this building are two-pipe, they would just, Andy Loftus down there, and he'd look at the weather reports, and all of a sudden he'd go, oh, it's getting really cold. Okay, he'd send the boys out, do the changeover Friday afternoon. And they'd come to all these buildings, and they'd go down there, and they're throwing valves, and they're doing all this stuff. So we're going to get hot water instead of chill water in that unit over there. Okay? So he'd done the change, and they really didn't want to go back to chill water and then turn around and go back to hot water, So it's kind of like you hold off as long as you can, but when you see a real cold front coming, you go, okay, change it over. And then, of course, 2 weeks later, it gets 82 degrees and everybody's calling like crazy. It's hot in here. Yeah, we've already done the change. Forget it. And he'd take a week's vacation because he didn't want to hear it, So now, in this day and time, we can do all this with computer controls. Okay? So, if you have the building automation system and all this stuff, you can fire the boiler, fire the chiller, but you got to be a little careful because you got one coil, you got one distribution loop. Well, let's say we've been heating because it was real cold at night. Well, so I've got a distribution loop that's 120 degrees. That chiller is not going to be happy if you turn around and slam 120 degree water into it. It's going to go, oh my God. And within 6 months, you've probably wrecked your chiller, And Carrier is going to come out here and they're going to see what happened and they're going to go, you've invalidated your warranty. We're not fixing this under warranty. You're an idiot. You can't do that. It's in all the requirements, operating specs and all that stuff. So then the automatic control system has to turn off the boiler, continue to circulate the loop until it gets down to whatever the desired set point is, 75 or 80 degrees. And then you fire up the chiller and you keep the valve shut on the unit. And then the chiller just cools down the loop until it gets it down to 42 or 44. And then the units can start cooling. And this process may take 3 or 4 hours. Okay. Now, could Tennessee Tech send its guys out every day to do that? Yes, they could. But how many buildings do we have on campus? And how many people do they have? You know, it's just not feasible. So, you know, that's what this changeover is talking about. Now, why would somebody buy a unit with just one coil? Absolutely. People making decisions are cheap. They don't understand. You know, who knows in this big scheme of the world who's making the decision on spending? It could be an entrepreneur. It could be a president of a university who doesn't know one HVAC beam from another. I mean, you know, who knows? All kinds of decisions get made. But usually it's expense because not only is it 2 coils, but it's 2 water piping systems. It's double pumps, you know. It's a lot of stuff doubles up, but it's a whole lot better. So there you go. So that's what this 2-pipe changeover is about. I didn't know I was going to run into that. Okay. All right, so we've got a unit. So let's simulate. Now, this is the design. Okay, I don't know that I've given you this. There's really 2 basic reasons to run this program. One is to size equipment. You know, you got a set of plans from an architect. You got to do the design. How many tons of cooling do I need in this room, what's this unit, what's the whole camp, you know, for the whole project, all that stuff. So that's design load calculation. The other path through here is for annual energy simulation. Most people probably run this for design, you know. I mean, in the years that I was getting paid, and this was the program I used for sizing equipment, I bet I didn't have more than 3 or 4 jobs in 15 years where people actually wanted to see projected utilities. You know, occasionally it would come up. This day and time, maybe more, I don't know. I've not been doing much of this for probably 10, 12 years. So I'm a little rusty. But okay, so you pick whichever system you want to see. And again, there is no run button. Right click, right click, right click, right click to run something. So I get up here, I right click, and it says print view design results. Bingo. And this is looking at different reports. These are the 2. I mean, if you want to see a site chart, we can show you a site chart. What is it? No, let's see. Hit preview. Bingo. There we go. Okay. Let's see. I think I can make that a little bigger. There we go. Okay. So got a E-system, chill water air handling unit, air system type, single zone, constant air volume, 1 zone, square feet, Nashville. I did the whole year. The different settings that it used for the simulations. 18 tons. There you go. So I'm sitting here looking at that, and I mean, you know, if I'd studied all this over and I thought I had a good simulation, what are you going to put in? Can you spec an 18-ton? Well, for an air handler, you probably could. If you're doing like packaged equipment, probably not. You probably put what, a 20? Might put a 20. If you don't really have much confidence in some of this stuff, you could put a 22.5 ton nominal. And then when you get into selecting, that's a particular size. Then based on the parameters, you get a more detailed number of capacity. But anyway, so 18 tons. So total coil load is 215,700 BTUs per hour, and the sensible portion is 158,700. So the difference between these is the latent load. It's latent plus sensible is total. Okay. When does it occur? July, 1,500 hours. 12, 13, 14, 15, 3 o'clock in the afternoon on July. East side of the building, I can believe that. You know, you want to look at that, because if it tells you, you know, midnight in January, you go, I don't think so for my cool. Well, something messed up, you know. Okay. Outside air, dry bulb, wet bulb conditions when this occurred. Entering. This is entering the coil. and this is leaving the coil. Apparatus dew point, 52. That's a coil factor. There's your bypass. Resulting relative humidity, 50%. Pretty good. Design supply temperature, 55, and all this. And so you can see it'll give you CFM per, let's see, I'm sorry, square feet per ton. Okay. Square feet per, you know, some of these numbers are what you look at to see if you kind of pass some sanity checks. That's actually a lot of square feet per ton of cooling, 645. So when I saw that, that would perk my ears a little bit. I would typically want to see that number down, you know, 400 or 500, something like that. But now, you know, I've got some glass. I don't have a whole lot of glass. I don't have a whole lot of people. You know, I don't have real concentrated loads in here. So then, you know, but so that would pique my interest a little bit. Here's your heating. Occurs, design heating. It doesn't give you a time on that, but there's 227,000 BTUs an hour. Okay. There's your ventilation load, outdoor ventilation data. Now, this is where the rubber meets the road. This is the detailed breakdown of all of those loads. Window and skylight loads. So 480, say you got square feet of windows. So you know how many windows, you know the size of the windows, you can get your calculator real quick and say, okay, do I have the right amount of glass area? Important parameter. Wall transmission, roof transmission, window. So see, the total window load is the sum of the first and the fourth item. That window transmission is the conduction loss, just based on indoor-outdoor temperature difference. It's not squat. What about the solar load? Solar load, 18,725 for 480 square feet. The wall transmission is not even 11,000 for 3,870 square feet. How bad do windows suck as far as heat gain? They're awful, and that's a good double pane window. And these architects, what do they want to do? They want to put flipping windows everywhere. They want to build an edifice, a monument to themselves. And then you have to provide the heating and cooling for their monument. And the more glass and the more whiz-bang stuff, they want to put a fountain in there and blow moisture up in the air. And they want to have all this plate glass window on the front. It's gonna face south or east or west. It always does. And the sun's gonna come roaring in. And then when they get the bid back on the HVAC equipment, they go, that's $225,000. We can't afford that. We'll take out some of the glass, idiot. You can't tell them that because they're the boss. They hired you to work for them. So you go, no, I got to keep my mouth shut. Peter, if we didn't have so much glass up there, maybe it wouldn't have to have so much air conditioning. I don't want to hear it. The wonderful relationships. But, you know, so you go down through all of these lighting and you can see, you know, sensible, you know, we've only got two contributors to latent load. We got what? People and infiltration, okay? And see, the infiltration number appears. If I don't click that button, 9 times out of 10, these numbers will be 0. And I'm sorry, that just irritates me, so I click the button. Okay, you can put safety factors in, you know. I mean, sometimes people get this, run it straight, and then just round up to the next larger size unit. You could put a 10, 15, 20% safety factor, and it'll, you know, the displayed loads will then be increased by that amount. Okay, what else we got? Don't have a return fan. There's my ventilation load. Yeah, see, there's additional latent. So see, the infiltration, that's air that leaks in through the windows. The ventilation load is brought in through the unit. And see, so say you have space loads and then you have other loads that appear just on the coil, because like that infiltration air and this supply fan, it's not in the space, but it's load that gets to the coil. So say your supply fan load here is what, 5804 BTUs per hour. So that's not quite a half a ton. What, 6,000? A ton is 12,000 BTUs per hour is a ton of cooling. Okay, if you don't know that. And so, yeah, you need to know that. Everybody out there and, you know, on the video recording, write down 12,000 BTUs per hour equals 1 ton of cooling. And that comes from the days when the ice truck used to run. So the ice truck used to run every 24 hours. So if you take a ton of ice, that's 2,000 pounds, and the heat of fusion or melting on ice is 144 BTUs a pound. Okay, so if you take 2,000 pounds times 144 BTUs per pound, that's how much you can absorb, and the ice truck runs every 24 hours. Divide it by 24, guess what? You get 12,000 BTUs an hour. That's my favorite unit, because you can talk about the old ice box that your grandmother had in her basement, where she used to take a block of ice and put down on the bottom, and it would melt drip into a tray, and it would keep all the food cold up above it. Okay, so, and I don't know, what is this? Oh, this is psychometric stuff, and I don't know. But anyway, those first two, to me, these were the two that I used when I was really doing design. I would pore over this. Because see, you got to make sure if each one of these categories is right, and you have included everything of importance in the building, then you got a pretty good load. And this is kind of summarizes what happened on the detailed sheet. Okay? Now, you can, if you click this, you can save this, save report as, and it'll save it as a .rif, which is a Word format. And so that you can open that in Word and do whatever you want to. So that's pretty good. Let's see. Okay, the other thing you can do, if I right click, you can do some simulation here, but you will not get any cost. You will not get any cost information. Tables. I don't know. I don't usually look at this, but we can do it. Let's see what we get. Yeah, so you get loads. What's that? Kilowatt hours, thousands of BTUs, that sort of thing. So you get energy, but you don't get cost. Okay. You have to define a building where you put the utility rates in to get cost. So I've never particularly used this. I'm not saying it's not useful, but I have never really used it. Okay. So then let's go to plants. Okay. So we have to have a hot water system because we're heating with hot water. Okay. So it will give you an error if you don't have a hot water boiler. And you can call that up. Systems, this hot water boiler is providing heat for all of my air handlers, so I have them all in. And notice you can put multipliers on these things. So if you had systems times 10, you could put it in that way. Service hot water, I've not put in. That would be for domestic hot water, hand washing, you're doing any clothes washing, something like that. Configuration. Auto size capacity, so I don't have to put in a size, it'll auto size. And I'm just going to put in 1. If you could put in 2 or 3, and then you could describe how it divides the loads between the boilers, that sort of thing. Schedule of equipment. And I can actually define a new boiler right here if I want to. So I have a steam boiler in here, but that's not the one that's in my hot water plant. And it's auto sizing, so estimated maximum load there, gave you an estimated distribution. Let's see, primary only, constant speed, what is this? Primary only, variable speed, primary, secondary. Yeah, that's a long discussion. Not gonna get into that. What are we pumping? Just fresh water. You could probably do glycol. You can do different glycols if you got freeze protection in it. Coil delta T, 20, I just let this define. I don't have a pipe heat loss factor. Pump performance, feet of water. I did stick in this. I've got 20 GPM flow rate. I don't know, I guess I stuck that in, I don't know. I don't remember now. Feet of head, pump efficiency, and motor efficiency, that sort of thing. So it needs that to calculate operating costs. Water source, I don't need. It'd be for, I guess, like for a water source heat pump. Okay, so how are we doing? We'll just run this. This is going to run over to next time, so I'll finish up the utility, putting in utility rates, and we can look at a rate similar to the one you have to, because that one you have to put in is fairly detailed. Oh, and I will say this, on your rate, you've got the COVID credit. You don't have to put in the COVID credit in your homework. That's in that rate file that I sent. And we'll have to figure out what to do with that TVA grid access charge. I'm not sure if that's going to fit the input structure of this very well. We'll have to figure out what to do about that. But at any rate, so again, this is my building. Let's see. So what have I got in it? Okay, I'll put the centrifugal chiller in. I'll take the screw out. So this would be for base case. Yeah, be sure don't run the screw for, I've got a screw and a screw. I got all this crap in there. All the systems, miscellaneous. This would be for other energy that you want to get on the utility bill. It could be parking lot lights. It could be you got a little shed back over there with a space heater in it, but you want to be sure and get that. If you're trying to simulate an actual utility bill, then sometimes you have to put additional loads onto it that are not directly in the building. And so you can do that here. And then here's my meters. And like I said, we don't have time. I do have some, these are left over from previous years, so that'll need to be looked at. But just to, so you get your meters in there, and then you right click on the building, simulation results, and preview. Okay. There we go. So I think we may have run this the other day, but we got pretty, I don't know. There's probably a little different numbers because I changed chillers, but you can look at this. Let's see, you can get, if you go all the way down to the bottom, let's see, we can get, if you ask for electric bill details, you can get, let's see, monthly energy use by type. There you go. So this is the detailed bill. So you see energy charges, demand charges, customer charges, and taxes. And it adds it up for the whole year. So if you get that rate structure in, you know, pretty much right, it's possible to match a utility bill pretty well if you get everything. Of course, it's a challenge. You know, you just go get plans on a big building someplace and they say that's already built. You go look at it and they give you the utility bills and say, here, we want you to match these. You go, oh, okay, this sounds like fun. So sometimes you can get pretty close, but sometimes it's an exercise in frustration too. But anyway, it gives you average kilowatt hour consumption totals, kilowatt hours, KW, demand for the month. So anyway, you have to, let's see, when you do the simulation, let me go back to, let me see now. Here, let me go back here. Yeah, I'm rusty. Okay, right here. You can only request the details on either the electric or gas. I don't think you can request them on the same run, but I mean, you can run it twice and one time get the electric and one time get the gas, just leave everything else the same. But, and then you can get tables, graphs, all this sort of thing. You can give it, you can look at a day or a week or a month or something like that, and it will add that to the output. So lots of really pretty good capabilities here. Okay, I think I probably harangued you enough for one day. So I'm going to save this away so we can come back here and then start looking at that, trying to just get in there, punch around, do some simulations, make sure you can get this thing running. I find this to be a really good tool because as you look through all of those inputs, don't hesitate to hit that F1 key and read about it because there's a tremendous amount of HVAC information and knowledge that goes into being able to intelligently run this software. So it's kind of a good platform to spur conversation and to get, you know, and I want you to run it enough that when you leave here, you feel like you have a tool in your toolbox that you could potentially use for somebody. Okay, I'm gonna cut it off there. Looks like we made it through okay on the record. So appreciate everybody's kind attention. And I will see you all next time.